If you clicked on this video to watch me walk through examples, you should skip to the time displayed on the screen, otherwise you can continue listening. For integration by parts, what we are essentially doing is choosing a part of the integral that's easy to differentiate, which is going to be u, and a part of the integral that is easy to integrate, which is going to be dv. And there are ways that you can go about doing this. You can do this by inspection and simply looking at the integral and deciding which one is easier to integrate or differentiate, which may be easier for a given integral, or you can go and look at this acronym LI8. And so what this acronym does is it helps you choose what term you're going to use as u. So it gives priority to logarithmic terms such as ln of x, and then to inverse trig terms like arcsine of x, algebraic terms like x cubed, and so on. So what essentially happens is when we choose u, as you can see here, our u comes out straight here, but also we have this du, which is the derivative of u. So why this makes sense to choose something for u that's easy to differentiate is because in our answer, or in the form that we're going to convert the integral to, we have u in its original form and in its differentiated form. So therefore we would want to differentiate u, and we'd want to choose a thing that's easier to differentiate for u. Likewise for dv, we want something that's easy to integrate, because dv integrated is just v. And here we have both v's here. Okay, so let's go on to examples. So the first example we have is the integral of x e to the power of x dx. Now we're going to choose our u's and our dv. So u is equal to the part that is easier to differentiate. And now e to the x differentiated is just e to the x, so that's quite easy. But now x differentiated is just 1. So that's probably a little bit better because you're left with a simpler term once differentiated. And then for dv, a part that's easier to integrate, now when we integrate x, it becomes x squared, which is slightly more complicated. And when you integrate e to the x, it remains as e to the x. So you can see that we're either choosing really between x becoming x squared and x becoming 1. So usually we would choose x to become 1. So our u is going to be x. And then our du is just going to be dx, because the derivative of x is just 1. And then for dv, that's going to be e to the x dx. And then when we integrate that, we're just left with v equal to e to the x. Now we can continue with the integral. So u dv, the integral of u dv is equal to uv minus the integral of v du. So now we have uv, which is x e to the x minus the integral of v du, which is e to the x dx. And then we can solve this. So x e to the x minus, and this we simply know as e to the x. And don't forget the constant of integration. And that's the final answer. So we'll move on to the next example now. And this will be the integral of x cos of x dx. So now again, we need to choose something that's easier to integrate and something that's easier to differentiate. Now we're faced with something similar as last time, where cos of x doesn't really become necessarily more complicated or simpler if we integrate or differentiate it, because it goes to sine of x either way. And it just means it goes to a positive or negative sine of x each way, which it doesn't really complicate it all that much. But x is the one that really decides our u, because x either goes to x squared over 2 when we're integrating, or it goes to 1 when we're differentiating. So we choose our u to be x, and we also, if we remember our LI8 acronym, we have a trigonometric term and an algebraic term. Our trigonometric term falls below our algebraic term, so we choose x to be our u. Okay. And then the derivative of u in terms of x is just 1. And then for dv, we choose that to be cos of x dx. And then the integral of that is sine of x. Now, if this form doesn't really make sense to you, I'd encourage you to think of it in this way. We take the dx across, and what we have is du dx equals to 1. And that should be a recognizable form of differentiation for you. And now if we were to integrate both sides in terms of x, you'd notice that we just get u, because those cancel, and then we get the integral of 1 du and here we're doing the integral of 1 dx. So 1 becomes u, and 1 becomes x. So this is really just another form of expressing this stuff here. It's not really that complicated, it's just so that we can take our dx across, rather than having it under here. Okay, so if we continue with this integral, uv is x sine of x minus the integral of v du, which is sine of x dx. And now we know that the integral of sine of x is going to be negative cos of x. So a negative times a negative is going to be a positive. Then we say cos of x because of this negative here, plus c, the constant of integration. So here's another example, the integral of ln of x dx. So this may be confusing because it doesn't really seem like there's more than one term in this integral, it's just ln of x. However, we can insert a 1. And now we get to choose which part is easier to integrate and differentiate. Now if we look at our LI8 acronym, it's clear that we're going to choose u to be the logarithmic term, which is just ln of x. So we can go ahead and do that, and I'll explain why as well. So, the reason why we're choosing the u to be ln of x, or ln of x to be the part that is differentiated, is because if we chose ln of x to be the part that's integrated, we're back at square one, which is the original question. So we're not going to go and do that. So, the derivative of ln of x is just 1 over x dx. And then dv is obviously just the term 1 dx. So therefore, our v is just equal to x. And you can check backwards if you want. By differentiating v in terms of x, you get 1. Okay, so our integral is then uv, which is ln of x times x, minus the integral of v du, which is x times by this here, which is 1 over x dx. Those x's cancel, and we're left with x ln of x minus the integral of 1 dx, which is equal to x ln of x minus x plus c, the constant of integration. And that's the final answer. Here's another example, the integral of ln of x over x squared dx. So we're going to choose something that's easier to integrate and something that's easier to differentiate. Now, using the acronym LI8, it's clear that ln of x, our logarithmic term, is going to be u, and 1 over x squared dx is going to be our dv, or the term that's easier to integrate. So, if we differentiate ln of x, it's just 1 over x dx, and if we find the integral of 1 over x squared, we'll just write this in another form to make it easier for us. X to the negative 2 dx is just x to the minus 1, minus x to the minus 1, because we increase this power by 1, and then we divide by the power. Now, our integral is ln of x times by minus x to the minus 1. Now, this here is also 1 over x, but there's a negative, so negative 1 over x. So we can just rub that out and put it as ln of x times by negative 1 over x, which is also just ln of x, negative ln of x over x. Okay, now our v du, which is this, and as we already said, it's negative 1 over x, v times by du, which is this, so we have that times by 1 over x dx, and this simplifies to 1 over x squared. And this negative we can take out, and which makes this a positive here. Okay, so now we say the negative ln of x over x plus, and we do the integral of this, which is what we've already done over here, if you see. So we get minus 1 over x, and then plus c, the constant of integration. Alright, so let's do another example. The integral of x over 10 to the power of x dx. Now, using our Lie8 acronym, we have an algebraic term and we have an exponential term. And since the A for algebraic comes before the E for exponential in that acronym, we're going to prioritize the algebraic term as a term to differentiate. So we choose u to be x. So we say u is equal to x, and then obviously dv must equal to 1 over 10 to the power of x dx. So the derivative of u in terms of x is just 1. And then the integral of dv, this here, we see it as. Now this is slightly complicated, but if we look at it, we know that if we're going to differentiate 10 to the power of x, we're going to be left with another term of 10 to the power of x times by ln of 10. And I'll explain all of this just now while writing it down. But also, so integrating it and differentiating it, you're going to have 10 to the power of x left over. So an easy way to think about it is to just say y is equal to 10 to the negative x, which is what this essentially is. And then if we differentiate that in terms of x, we get it's ln of 10 times by 10 to the negative x. Okay, now if we want our final answer to only be this, if we're going to integrate going backwards, you see, we take this dx across, we only want this. You can see that's the same as this. dy is the same as dv. 10 to the negative x is the same as 1 over 10 to the x, and dx obviously the same as dx. So we want to have only this part of the integral. So we don't want this ln of 10 here. So that means our answer is going to be negative 10 to the negative 10x, sorry, this is a negative here, over ln of 10. And to check this, and I've divided by ln of 10 because I don't want it, you see. So, to check this, we differentiate v in terms of x. And the derivative of 10 to the negative x is negative ln of 10, negative ln of 10, and that negative, so I'll write here, dv is equal to negative ln of 10 times by 10 to the negative x dx, okay? But now we also keep our constant there, which is negative ln of 10 here. And those two cancel, and what we're left with is dv equals to 10 to the negative x dx. So we see that our integration worked. Okay. So now we have uv, which is just going to be negative x times by 10 to the negative x over ln of 10 minus the integral of v du, which is minus 10 to the minus x over ln of 10 dx. If we just write this down quickly. Now we have to integrate negative 10 to the negative x over ln of 10. And we've already seen that when we differentiate 10 to the negative x, or when we integrate 10 to the negative x, we get this. And now if we're going to integrate 10 to the negative x again, we'll get the same thing. So, what I'm saying is, originally, we just integrated 10 to the negative x. Now what we're going to do is we're going to again integrate 10 to the negative x and then multiply it by the constants. So we're going to have this multiplied by the constants. Now the reason why I'm referring to this here is not because it is necessarily always going to be the answer down here, but it's because in this particular case, I can use it to my advantage instead of doing a difficult integration again, or one that's difficult to think about. I already have it written down, and I've already fact-checked it, so I can use it. So the integral of 10 to the negative x is going to be this, and I'm going to times it by the constants. So the negatives are then going to cancel. These negatives are going to cancel, and this ln of 10 is going to be times by itself to become ln squared of 10. So we're going to be left with this negative will stay, but this negative will go because it's times by the negative. And then we get over ln squared of 10, and then 10 to the negative x, and then plus c. And that's our final answer. So this may be quite difficult to think about just because of this integral here. But if you keep it simple and then check backwards, you can always know if you've got it right by differentiating v to see if you've integrated dv correctly. So let's do one last example. The integral of e to the x sine of x dx. Now it's not necessarily easier to differentiate e to the power of x or sine of x, or to integrate e to the power of x sine of it, or sine of x. So it's quite tricky now. You think, which one should I choose to be the u and which one should I choose to be the dv? And now in this particular instance, it doesn't really matter because you'll end up at the same point later on. So we'll choose u to be e to the x, and then our du is going to be e to the x dx. And obviously if you're stuck with the Lie8 acronym, it would still work out. So now you might be saying to me, well, it doesn't really make sense because in the Lie8 acronym, the trigonometric term is prioritized over the exponential term, but now you've chosen the exponential term to be my u. Well, it doesn't really matter for the reason that I've just explained, as in that neither of them are really more simple or more complicated to differentiate or integrate. So if I carry on like this, and I'll show you that it still works, and then you don't really have anything to worry about. And if you want to try it yourself, you can go ahead and do it the other way by choosing u to be sine of x and by choosing dv to be e to the x dx. And you'll find that you get the same answer eventually, and it's not necessarily harder. So our dv is sine of x dx, and the integral of sine of x is just negative cos of x. Okay, so this is equal to e to the x times by negative cos of x minus the integral of v du now this negative can come out and make that positive. Now you see this is really similar to this, so we're going to integrate it again with another integration by parts, and we'll see what happens. So we'll take u equal to e to the x again, and du equal to e to the x dx. Then we take dv to be cos of x dx, and we take, and then our v, when we integrate dv, is just going to be sine of x. So now, if we continue with the integral, we're going to keep this term, minus e to the x cosine of x, plus now uv e to the x sine of x minus the integral of v du, which is just e to the x sine of x dx. Okay, now you think, okay, well, now we're just going in circles because we've got this integral and that was our original integral. But now, if you actually think about it, that's very, very helpful, because now we have this on the left-hand side and the right-hand side, so we have the same term. So if we label this I, then what we have here is I is equal to this, but this here is also equal to I. So we can erase all of this and just put I. And now what you'll notice, which is very clever, is if we take this I across, we're left with I plus I, which is 2I, equal to minus e to the x cosine of x plus e to the x sine of x. Don't forget your constant of integration. And now we just divide through by 2. So our original integral, e to the x sine of x dx, is equal to minus e to the x cosine of x over 2 plus e to the x sine of x over 2 plus c. And now I don't really have to divide c by 2 because c is an arbitrary constant and we don't really know what it could be or what it is. We know what it could be. It could be any real number. But c, we don't know specifically what it is. This is just an indefinite integral. So it doesn't have an assigned value. So it doesn't matter if c is represented as c or c over 2. It's arbitrarily the same thing.